This video is for lesson 9-4, rotations. The learning goals are to perform rotations on and off the coordinate plane and to identify and distinguish between reflectional symmetry and rotational symmetry. So let's continue this example of the marching band. For the big finish of the Marching Cougars performance, Mr. Scott arranged the band in a triangle formation. Then the triangle appears to rotate clockwise around a point like a pinwheel. The center of the rotation is the vertex located at 0, 0 of the coordinate plane. So this first drawing shows the initial triangular arrangement of the band members. A little bit later on, after they have moved like that, the triangle would appear like this. And then a little bit later on, they're going to continue that rotating or pinwheeling motion, and the triangle arrangement of band members would appear there. This spinning type of transformation is called a rotation. It is defined by the center of the rotation, which is mapped to itself, and the angle of rotation. The center of rotation may be part of the figure being rotated, as in the case above, or it may be a point outside the figure. Notice in this example, the center of rotation is that point 0, 0. The person standing at that spot doesn't ever move when the rest of the triangle is rotating around. That person stays in that spot. That's the center of the rotation. Functions that describe rotations include these examples. X, y goes to y, negative x. Notice how these coordinates are being manipulated. Whatever this first number is, whatever this second number is, they end up in different positions, and even the sign changes on this coordinate. And this corresponds to a clockwise rotation of 90 degrees. That's this first movement in the drawing above. When the triangle originally was here and a little bit later is here, this is a clockwise rotation of 90 degrees. Look what happened to the x and y coordinates of points. Just as a quick example, look at the band member standing right here. Maybe this is the tuba player. This person is at 0, 10. This person ends up here at 10, 0. So there has been a change in the coordinates, right? If you repeat that function twice, it produces x, y goes to negative x, negative y. This is a rotation of 180 degrees. This is this third picture when compared to the very first one. This triangle has rotated clockwise 180 degrees, a half turn, and ended up like this. And the coordinates of all these different people in the band are all adjusted, except for that one guy at the center. This last example, the function x, y goes to negative y, x, is a clockwise rotation of 270 degrees, or 3/4 of a turn. Moving clockwise 270 degrees is the same thing as moving counterclockwise 90 degrees. Number 1, complete the table for the two rotations shown above. So in this column here, we have x, y goes to y, negative x. This is describing what to do with the ordered pair to create our ordered pair answer. We need to first reverse the y and x positions, then also take the opposite sign of the x. So 3, 10 would become 10, negative 3. Negative 3, 10 would become 10, positive 3. Again, I'm following what this function rule is telling me to do with the x and y coordinates. 0, 0, however, will just stay as 0, 0. This other one here, x, y, goes to negative x, negative y. I just have to change the sign of x, change the sign of y. No reversing of the positions here. So 3, 10 would become negative 3, negative 10. The negative 3, 10 would become positive 3, negative 10, and so on. Use the figure for items 2 and 3. So we have this arrow-shaped figure drawn on the coordinate grid. And number 2 says predict the direction of that arrow after these rotations. Assume the center of the rotation is 0, 0. So let's make the origin our center and we'll rotate around that. We're going to take that arrow and rotate clockwise, or if it says counterclockwise, we'll rotate it that direction. Imagine in your mind this arrow turning on the screen. So if we go 90 degrees clockwise, I think it will point to the right. If we rotate 180 degrees, so take that arrow, turn it, turn it, turn it, turn it, turn it, turn it, 180 degrees, I think it's going to point down. And if we go 90 degrees counterclockwise, I think it's going to point to the left. Now, number 3 says to draw these rotations up on the grid to see if we were correct. Let's start with question A, a 90 degrees clockwise rotation around the point 0, 0. Rotations preserve distances. So when we measure from the center to any point on that arrow symbol, when we draw our image, it's going to have that same distance. So for example, this person at the very tip of the arrow, it is 10 units from the center to get to that spot. Imagine it rotating clockwise and that person ending up right there at the 10, but on the x-axis. That's that idea of reversing, the number that was the y-coordinate with now the x-coordinate when you do a clockwise rotation of 90 degrees. Where are some of these other people on the arrow going to end up? For example, this bottom section of the arrow, there's probably a person here, a person standing here, and maybe some band members kind of in between. If that thing rotates clockwise 90, I think it's going to end up looking like this. Okay, this little piece of the arrow here, right? This dash mark right there is at 6. So when that rotates clockwise, that's going to also occur where the 6 is. I think that arrow is going to end up like this. And then it's going to come up there. And it's going to come across here. And then there will be the little dip part of the arrow. And then now the pointed part of the arrow. How does that look to you? Does that look exactly the same size and shape as the original arrow, but rotated clockwise 90 degrees? The way that I did that was to carefully measure distances from the center to various points on our figure, and then to redo those distances, but now moving along the x-axis. So there's question A. Now the one for 180 degrees. If you rotate that all the way around, I think it's going to now exist down here and be pointing downwards. So let's carefully measure distances. That's just what? Just that 1 unit there. So if we go just down the 1 unit, there's that part of the arrow. And now the next piece is going to come down like this, and like this, and then the over and the overs, making kind of like the shoulders of the arrow. Remember how that was at 10? So this one here is going to be at the -10. How does this look to you? Did I do a good job of keeping it exactly the same size and shape as that original? Okay, and finally, question C, the 90 degrees counterclockwise. So spin it around this direction. So kind of the same idea as our first one, right? But pointing over this way. So we have this piece here of the arrow, and then it comes across to there, and to there, and now the little shoulder parts. And then here's that point, right, at the -10. And then to finish it off, there we go. So here are our 3 answers for A, B, and C. Were our predictions correct? Yep, I think we did pretty good on those. Number 4, describe the rotation that maps figure A, that's this rectangle standing kind of vertically, onto figure B, and hint, first identify the center of rotation. The center of rotation is that point that maps to itself, so it's in the same location in the image as it is in the pre-image. And I found that here and I marked it with that purple dot. I think it's that point that doesn't move. In If I imagine rotating figure A so that it now lands where figure B is, I think that's the corner of the rectangle that does not move. Do you agree with that? And so I think that this rotation is a 90 degrees clockwise around the point 1, 0. This dot right here is 1, 0. Question B, similar question. Here we have triangle A. How can we rotate this so it lands here? Well, we could do a 3/4 turn, 270-degree turn around the dot, or a little bit simpler, how about a 90-degree counterclockwise turn? But I have to know where's that center, right? So where's the dot that I rotate around? And so to find it, I kind of dropped down from the center of that shape and then came across the center of that shape, right? There's a nice 90-degree angle right there. And then this dot is at 1, -2. That's my center. The angle of rotation can be used to describe the image of every point of the figure. Consider the rotation shown below. Rectangle ABCO, this one here on the left, is rotated 90 degrees clockwise and maps onto rectangle A prime, B prime, C prime, O. That's this one here. From the diagram, it appears that segment AO, right there, is perpendicular to A prime O. There's a 90-degree angle there. And that segment CO, that's this one, is perpendicular to segment C prime O. Right there, it's 90 degrees right there. If you measure angle BOB prime, B to O to B prime, this angle, it's going to be 90 degrees. The following figure is a square that is centered around the origin O. Point A is one vertex of the square. Here's point A, the top left corner of the original black square. Imagine the purple's not there yet. Question 5. Draw a rotation of the square 45 degrees clockwise about the origin and label point A prime. So to do this, I connected A to the center O. And then clockwise, or to the right, I figured out in what direction 45 degrees would be. And that required me to move upwards, just right up the y-axis. My only other concern was to get the distance correct. So first I found the distance from A to O. I used the Pythagorean theorem. If this is 3 and this is 3, I did 3 squared plus 3 squared and then did a square root. I found this distance. It was 4.2. So I measured up 4.2 to put the dot for A prime. And I could do that for all the other 4 corners of the square as well. That's how I drew the purple square for question 5. Now, what is the measure of angle AO, A prime? This one here in brown, 45 degrees. I actually used that angle to help me make that drawing to begin with. Like translations and reflections, rotations can be defined independently of the coordinate plane. A rotation that maps point P to P prime and point Q to Q prime has the following properties. Assume point O is the center. First thing, this is saying that those distances are equal. We used that idea in that previous question, that this distance from A to O was equal to the distance from A prime to O. So that's something true about rotations. Distances are maintained. The other thing that's true is that angles, these angles are congruent. In our example, this angle here in brown, the 45-degree angle, is going to be congruent to, like if we had done another corner, right? If instead we had taken that corner of the square and gone to the center and then measured 45 degrees and then, came out in that direction to find this dot, that those are going to be 45-degree angles, that those are congruent. To describe rotations, we will use these symbols. So the capital R means rotation. Remember, a lowercase r meant reflection and a T meant translation. The subscript has two parts. The first thing is going to be the center of rotation. So in our example here, that's O, but that's going to mean the center of rotation. Comma, and then the degrees of the rotation. For instance, 90 degrees, 180 degrees, whatever that might say. So these symbols are saying rotate point P around point O this many degrees, and that maps to P prime. Number 11, the diagram below shows isosceles triangle ABC and point O inside it. Draw the following rotations and label the images. Let's start with question A. We want to rotate around point O negative 90 degrees. So counterclockwise, go this direction. Remember that distances are maintained. So doing this on paper, we should be using a ruler, but again, I can't easily do that on the video. I want to find this distance with a ruler, and then I want to make a 90-degree angle here and come out exactly the same distance. I want these to be equal because that's how I'm going to find A prime. We can do that for every corner of the shape. Okay, so from O to B, however far that is, right, find this distance. And then remember, we're doing counterclockwise, so we're twisting it this direction. So I want a 90-degree angle right there. I want it 90 degrees. I want to come out this direction the same amount with a ruler to mark point B prime. Same thing for C, right? If you go from C to the center, measure that with a ruler. Make sure you make a perfect 90-degree angle right there and come out that direction until you get to C prime. Connecting these together carefully will create our triangle. It should be exactly the same size and shape as the original, but it is rotated 90 degrees counterclockwise. There is question A. All right, I've cleaned that off. Now let's try question B. Rotate around point C 90 degrees. Around point C. So here's point C. This is our center. We're going to connect everything to point C and go 90 degrees clockwise. So for example, the center of our triangle will rotate. So if we connect O to C, measure that distance with a ruler, and go 90 degrees, this time clockwise, so we're turning it in this direction. So when we create our 90-degree angle, we want it to bust out that way, right? Perfect 90 degrees. Go that same amount. I want these to look equal. And mark it, and there's where O prime is. That's going to be the center of our new triangle. Okay, the same thing for every other corner. So from B to C, that's this distance. And then it's going to come up this direction. Right? And there is B prime. C is just going to stay where it is. But let's do A now. So from A to C, and then make a 90-degree angle right there as you come out this direction. However long AC is, make this distance exactly the same, and there's A prime. Then when we connect these, we will have our rotation. Should be exactly the same size and shape as the original, but it is a 90-degree clockwise rotation around point C, not around point O. Okay, next, let's do a rotation around point A of 90 degrees. Okay, that other one's cleaned off. We're going to rotate around point A, 90 degrees. Again, this is positive, so clockwise. Let's connect everything to point A. So there's that. Again, we're rotating clockwise. So our 90-degree angle has to be there. If I swung it around this other direction, that would be a counterclockwise twist. Okay, so we come out there, equal amount. We want that to be congruent to that. And there's how we find O prime. Now let's connect B to A. That's this side of the triangle. And then make a 90-degree angle there. Okay, that angle, 90 degrees, is what we're shooting for. So it comes up here. Again, I want this distance on a ruler to be equal to this distance. And that's where B prime is. Okay, from C to A, that's this side of the triangle. And then 90 degrees. Again, it's getting kind of cluttered in here, but I'm trying to get a 90-degree angle between that side and that thing right there. I want 90 degrees. So I'm coming out here to find C prime. So then connecting in brown, get something like this. Should be exactly the same size and shape as our original triangle. I can see already this is a little long compared to what this looks like to me. It's because I wasn't using a ruler, and I should be. Number 12, describe 3 rotations that would map a square onto itself. So if you had a square and maybe found the center of the square, how could you rotate that so that it just snaps back down onto itself so that the corner lands on a corner? I think there are 3 possibilities. We could rotate around the center 90 degrees. We could rotate 180 degrees, or we could rotate around the center 270 degrees. Review your answer to item 12. This idea about when you rotate a square, that there's times when it just lands back on itself. These figures have rotational symmetry, meaning that a rotation of less than 360 degrees can map the shape onto itself. The smallest such angle is the angle of rotational symmetry. Number 13, identify whether these figures have rotational symmetry, reflectional symmetry, or both. Also identify the angles of rotational symmetry and any lines of reflectional symmetry. So question A, an isosceles triangle. This does not have rotational symmetry. There's not a point somewhere in the center that you can rotate that thing and it will land back on itself, not without doing a full 360-degree turn. So no, there's no rotational symmetry. It does have reflectional symmetry. There is a line of symmetry right down the middle like that. Okay, question B, an equilateral triangle. Yes, that does have rotational symmetry. If we locate the exact center of it and then connect one vertex to the center, connect the next vertex to the center, and look at this angle that happens to be 120 degrees. If you rotate the triangle 120 degrees, that corner would land there, and that corner would land there, and that corner would land there, and the triangle would just look like it does now. So yes, it has rotational symmetry, a 120-degree rotation. Does it have any lines of symmetry? Yes, it does. Here is a line of symmetry, here is a line of symmetry, and here is a line of symmetry. Question C, how about this rhombus? Well, yes, it does have rotational symmetry. If you find the exact center and you were to rotate it 180 degrees, that rhombus would look just like it does right now. Does it have any lines of symmetry? Yes, it does. You could split it there, and if you fold it, it would line up perfectly, or you could split it here. So yes, it has lines of symmetry and it has rotational symmetry. Okay, last one, a regular hexagon. Yes, there is rotational symmetry. Find the center. Connect a vertex to the center. Connect the next vertex to the center. And what is this angle? It happens to be 60 degrees. Does it have any lines of symmetry? Yes, it does. You could split it there. You could split it right across there. You could split it right across, whoops, it's kind of bad, right across there. It could be split, right across there. Getting kind of bad on my drawing here. It could be split across there. And finally, it could be split across there. It has many lines of symmetry. Okay, here are some check your understanding questions, so I will pause the video. In this lesson, we did some rotations, first on a coordinate plane where you work with coordinates, but also off the coordinate plane where you're using a ruler and possibly a protractor to measure angles. And we identified and distinguished reflectional and rotational symmetry. Reflectional symmetry is when you can draw lines of symmetry, and rotational symmetry is when you're able to locate an angle that you can rotate and the figure would line back up on itself.